Hello there, ordinary little humans. Welcome to the twisted world, or should I say worlds, of quantum physics. There will be a test, so you'd better grab a pencil and start taking notes. Ha 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 ha! I'm just kidding. Luckily for you, there's a universe where you've already aced the test. But do put on your Viola 10 thinking caps as we delve into the science of quantum mechanics. But not in a dull, science-y way. In a fun way.
Say, how do you make science fun?
Why, by removing most of the science, of course. You see, kids, at the Viola 10 laboratories, we start with 100% boring facts and figures found in dusty old peer-reviewed journals at the Nerd Library. After skimming those for a good 20 minutes or so, we toss the books and come up with our own examples, like this one. If you pick up a rock and throw it, the rock will travel along a curved line until it comes to a stop in the grass or in the mud or hits your little brother in the face. Oop! Be a little more careful next time, Lucy. But if we look at things really closely, we find that everything's made up of tiny, tiny little pieces called subatomic particles. And these particles don't behave like the rocks here in the big world do. If you were small enough to pick up one of these particles and throw it like a rock, it might land anywhere. The rock might even end up throwing you. But that's the risk you take when you play in the quantum playground. Or maybe it's payback for hitting your little brother in the face. I told you to be careful. You see, this will be lots of fun, kids, even if nothing makes any sense at all. The world that we see around us is almost boringly predictable. The normal-sized world is ruled by Newton's laws, and normal-sized objects obey the law. But these objects are squares. Don't be a square, kids. Come with me to the quantum world. A world where, if you have a milkshake, you will probably not be able to find a straw. And if you find a straw, your milkshake glass is probably already empty. That is the quantum world of the Heisenberg uncertainty principle. Formulated by Werner Heisenberg in 1927, the Heisenberg uncertainty principle states that at the smallest known levels of existence, the more you know about something, the less you know about everything else. That's right, kids. The only rule is, there are no rules. Einstein was bothered by Heisenberg's principle. Einstein said, God does not play dice with the universe. Ha ha ha! Sorry, Albert. You can't be right all the time. The Copenhagen interpretation of 1927 states that subatomic particles exist in a superposition.
Say, what's a superposition?
I was afraid you'd ask. A superposition is when a quantum object is both a particle and a wave simultaneously.
Cool! Thanks, Mr. Wait, what?
Exactly. And dig this, you little hep cats. Observing the particle causes the wave probability to collapse to a single outcome. You see, particles act like particles when they are observed. Particles even act like particles if they are going to be observed in the future. But when nobody is watching, it is just one crazy hopped-up bacchanalian orgy. So sit back, relax, and let the waves and or particles of knowledge wash over and or smack you right in the brain. In 1935, Erwin Schrödinger kicked the world while it was still confused. Maybe he was putting a little too much devil's lettuce in his Brownian motion theories, if you know what I mean.
Yeah, Daddy-o, we're hip, we dig.
Really? Anyway, he came up with a very strange experiment known as Schrödinger's cat. A cat is placed in a box, along with a flask of cyanide, a hammer, a Geiger counter, and radioactive material with a 50-50 chance of being detected by the Geiger counter. If radiation is detected, the hammer smashes the flask and the poison kills the cat. If radiation is not detected, the cat lives. Until the box is opened, the cat exists in a superposition, both alive and dead.
Say, can I check on the cat?
Not so fast, Timmy. Your curiosity might kill that cat. You see, it is only the observation of the system that forces the wave function to collapse and forces the cat to be either alive or dead. The fate of the cat is intertwined with the observation of the system. Schrödinger described this relationship as Verschränkung, or entanglement.
Okay, well, bye, mister. We're gonna leave now.
I don't blame you, you little hooligans. Verschränkung, or entanglement, makes as much sense as a sandwich made out of soup. Einstein described entanglement as a spukhafte Fernwirkung, or a spooky action at a distance. That was Einstein's technical term. Am I the only one who's alarmed by that? Entanglement is like telepathy between particles. Let's say a small particle is split in half, and one half is taken to New York, while the other half stays in Los Angeles. If one of the particles is observed, the other particle will react instantly. Einstein's theory of relativity prohibits information from traveling faster than the speed of light. So how could the particles communicate? According to the theory of entanglement, the information does not travel. Rather, the particles are still connected. And time and space merely creates the illusion of separation. And since everything was connected at the time of the Big Bang, everything may still be connected.